I like that.
So, there was one problem I put on the practice test that I did not put on the test itself, but it's gonna come back. It's one reason why I put it on the practice test, was so that you had already seen this before. We're about to get into chapter 8, but I want to lay some groundwork. A lot of chapter 8 builds on stuff we already know, which is always nice. So let me ask you this question. Let me see if you guys can do this problem. Don't say anything. Just try to do this. Can anyone figure out the two z-scores that bound the middle 95% of a normal distribution, standard norm? Don't say anything. Just think about it. Quick little hint. Can I look 0.95 up in the chart? No. Is that area in a place the chart understands? The chart only understands areas that are below a z-score that I want, right? So you all agree with me there's two z-scores that up there that I need? Right? Okay. Do you also agree with me that since they bound the middle and the symmetry of the z-score chart, if this was negative 1, this would have to be 1. Does that make sense? So I really just have to find one of them. And again, to find it, to use the chart, I need an area that's below a z-score, and I want two of them. So either one will work. If there's 95% inside, how much is outside? How much is on that side? 2.5% or 0.025. Is that cool? All right, so look up 0.025. So verify that. So look up 0.025. Does it come out to be negative 1.96? Or you guys are like, that sounds good. You never know. You could be wrong. What's that?
That's right.
He's right, okay. So it is negative 196. So this would have to be 1.96. I love it. So what does that mean? If I start at the mean and I go up and down 1.96 standard deviations, how much data do I catch in there? 95%, right? If I did that, let's say this is the distribution of ages at Grossmont, right? And there's a specific person we're trying to catch. What's the probability that we caught them if we go here? If we catch those people? 95% chance, right? You guys, believe it or not, this directly ties into the whole idea behind chapter 8, which is where we're getting into, chapter 8. So far, so good? Let's try this one. Middle 98%. Search. So it's the same idea. What percent is outside? 2%. 1% on that side. Now real quick, let me do this a little differently. What area is below that z-score? 99. So if you look up 0.99 on the positive side, you should get the positive number of what you would get if you look up 0.01 on the negative side, right? Has anyone looked that number up yet? All right, negative 233. And you look up 0.99, you should get positive 233. So it doesn't matter which one you get. Two things working in our favor. If I know one, I know the other one immediately because they're positive and negative of each other, correct? Because of symmetry around 0. Is that cool? right? Secondly, the chart understands areas below, so I just need the area below either one of them, because once I get it, I know the other one. Is everybody with that? This is nothing new, right? Okay, I like it. Okay, now, what we're about to get into is we're getting closer to real life statistics. So one thing that is very not true to life in chapter 6 and 7 is most of the time when we're analyzing stuff in the real world, we don't have a freaking clue about shit. We don't know what the population mean is. We don't know what the population standard deviation is. Are you with me? So this morning I had this example of, and I'm just gonna stick with it. All of a sudden, I have no idea why, but the movie Arachnophobia came to mind. And there was a scene where they discovered this species of spider. Are you with me? So let me know if you're really, really not good with spiders. I can't even talk about it because I'll talk about something else. So let's say we would discover this new species of spider. Do we know the average weight of that population of spider? We've never seen this damn thing before. Are you with me? So what would we do to start gathering data about the species of spider? If we're curious about the weight for some reason, what would I do? That's research. I'd capture a bunch of them. Try to make sure that they were from all over, because what are we trying to do for a sample always? Make sure that it is random. So every time we talk about a sample, we understand it's a random sample. It's gotta be, or else the whole thing goes to shit. Is everybody with me? I like it. So we try to get a random sample of these spiders, get a sample mean. Because what's the idea? Go with me for a second. And you're like, that's all we ever do, Jeff. If I take a random sample of spiders and I get a certain sample mean, how should that relate to the population mean? Are they gonna be equal to each other? If I took a sample and got the average, would you put money on it being exactly equal to the population average? I would not. And not just because I'm a teacher, but because it's a bad bet. Are you with me? But if it's a good random sample, should we expect the average to be close to the population average? Yes, of course, especially if it's a larger sample. Are you with me? The larger the sample, the closer I would expect it to get. You guys sort of with me? Okay, I like it. Okay. So just finding a sample mean is not good enough to communicate to somebody how uncertain we are about what we're seeing. So chapter 8 is all about trying to improve on that one data point, that one thing, the sample mean. Okay, so what we do, we're gonna need you later. So, go on. These spiders, right, I'm not gonna draw a spider. These spiders, they have average weight. It just exists, correct? Right? Even before we discovered them, they had an average weight. It's just a number that nobody calculated yet, right? So they have an average weight. We come along and we take a sample of spiders. And let's say we get a mean, that is, we just happen to randomly get such a wide array of colors you have, Jeff. Black and blue. Okay, here we go. So how your students feel? Maybe. Okay. So let's say we get here, right? Our sample mean just happens to go there. We just happen to get some lighter spiders, right? Instead of heavier. You guys kind of with me? If I went up and down 2.33 steps from that sample mean, what percentage of the data should I catch? Especially if I tell you that the sample size is greater than 30. 98% of the data. How certain would we be that we caught the real mean then? What would the probability be that we caught the real mean in this interval? So let me ask again. What percentage of the data would I catch if I went up and down 2.33 standard deviations? Huh? 98%, right? Let me be really careful. And so what would the probability be? that we caught any specific data point. Just like earlier, that we caught one specific person. Same idea. How much of the data did we catch? 98%. So what's the probability we caught a certain data point? In this case, the mean. 98% chance, correct? So we would say that we're 98% confident that that interval we created catches the real mean. Can we stop for a minute?
Is that what they do like in like prescription commercials where they're like, oh, it helps like 98 point whatever % of people? Like,
Not really. Yeah, I'll show you. If they were really communicating a confidence interval, they would give a plus or minus. By the way, real quick, do any of you guys pay any attention, even if you don't want to? Do you happen across any information about elections and politics and such? Do you ever see stuff like polls where it says, oh, we think 44% are going to vote for Jimbo and 38% are going to vote for the other person, right? Have you ever seen those kind of things? At the bottom, if they show you all the information, at the very bottom of that, it should say, so here's Jimbo, whatever I said, I don't remember, and Rando, 48%. At the very bottom, it should say something like plus or minus 4%. I don't know if any of you guys have ever seen that. Okay. That's this basically, plus, minus, right? Give and take, maybe? So we're gonna actually see the math behind where that comes from, this thing that maybe most of you have never seen. Okay. All right, you guys doing all right? You all look very distracted. I'm sorry, I'll stop remarking a minute. Okay. So to do this, and let me show you another idea about what the 98% means. If another group of researchers came and gathered their own sample, they took their own sample, would their sample mean necessarily be the same as our sample mean? In fact, that I would put double the money on it being different. If two different groups take two different samples, I would put a lot of money on those two samples having different means, right? So let's say they come along and they take their own sample and they just happen to get a bunch of really heavy spiders. And when they make their confidence interval, it doesn't catch the real mean. Neither one of us knows that, by the way. We don't have a clue. Neither group knows the actual population mean. Of course we don't. We don't have all the spiders. You guys semi with me? Like this much? Are you with me this much? All right. Okay. So what this really means, in fact, you guys help me remember. 50%, I flip a coin. What's the chances it's a fair coin? What's the chances it lands on heads? 50%. What does that mean?
Half the time.
Half the time. If I flip it once, does that make sense?
Yeah.
Once, half of the time.
Oh,
No. That would mean that one half of a flip goes heads and one half of a flip. It doesn't make sense. So when do probabilities start making sense? If I do something a lot. If I flip a coin 1,000 times, right, what would I expect? How many heads? 50%, 500. Now it could be a little different from that, but I would expect 500. And then the deviation just depends on randomness, right? Are you guys kind of with me? So this means if I construct one confidence interval and we're 98% confident, that really means if 100 different groups constructed 98% confidence intervals, 98% of them would catch the real mean. Only 2% wouldn't. So how confident are we that ours catches it? 98%? Because there's only a 2% chance it doesn't. Okay, maybe. By the way, you're going to have to, you know what's happening, right? This has happened. We are in the discussion of concept right now, right? This is nothing about what you're going to do yourself for homework. You with me? We're just discussing the concept. We're going to make it more concrete here in a bit. Okay. All right. So we've already kind of talked about how far to go to capture such a percentage of the data. So now let's kind of start to get this a little more concrete. Yeah, okay. So if I remind you about this formula here. So if I wanted to make these both back into raw scores, like maybe spider weights, right? What would I need to know? I would have to know the mean and the standard deviation, right? If I wanted to convert both of these, wouldn't this be like mu plus z sigma and mu minus z sigma, sort of? I want to go up and down, is that all right? And I would do that every damn time because there's an up and a down part to these. Does that make sense? Okay, maybe. So that's the first thing I'm going to do is I'm going to make this plus or minus. Okay, so I'm going to mess with this formula a little bit. Now, if I just discovered some group of spiders, do I know the population mean? No. So the very first thing we have to do is I'm going to estimate mu, I'm going to estimate it with x bar. Okay. I love you guys. You all look tired. Is everybody with me? That must mean I took a sample, correct? So let's say my sample size is n, which is greater than 30. Now, one little thing we have to talk about here. So there are situations if I just happen across a bunch of spiders that I had never seen before, I wouldn't know their average weight and I wouldn't know their standard deviation of the weight. I wouldn't know either one. Section 8.1 deals with situations where we know the population standard deviation. So let me give you an example where that would make sense. Because normally what would make sense is we don't know shit, so we don't know either one of those. But let's start off with this. Let's say, I'm going to make this into a concrete problem later. I'm going to do the same problem I did earlier, because my brain can't come up with a different example. On an island somewhere, a lot of trees. And we happen to know the standard deviation of all the trees, right? I'm going to make it up later. We know the standard deviation of all the trees. And this is one little area of the island that we're a little concerned about because there was some dumping of something there or whatever. So we go in there and we measure the heights of the trees here. So this is a situation where we don't know the heights of the trees in this little area, but we do know the standard deviation of all the trees. Are you guys sort of with me? So there are situations where we know the standard deviation. For example, I know the standard deviation of male heights in America. It's a known number. But I could go to a small area in some state where I'm concerned about the diet or something, and I'm like, did it affect the heights? And I could just take a random sample of heights using the actual standard deviation of the population, and I could kind of make a confidence interval. So I really want you to understand, section 8.2 says, all right, we don't normally know the population mean, and we don't normally know the standard deviation of the population. That's going to be trippy. That's going to take a little bit more. So we want to ease into it. Let's just say, okay, there are situations where we do know this. Let's not make things too trippy yet. Okay, maybe. Okay. All right. So I'll make that into a concrete problem in a second. Coming back to this, if I did take a sample, and I'm talking about the sample means, what must happen here? Yeah, I've got to divide it by the square root of n to make it one that works for groups. I like it. Okay. So what this formula does, this creates the interval I was talking about. If I start at the mean and I go up and down this many steps, I will capture a certain amount of data that will create that confidence interval that I was talking about. Okay, maybe. So what this formula does is it kind of captures the real mean. So let's try this concrete problem. Let me make this into a concrete problem. Let's say that the standard deviation of trees on this island is known to be 2.91 feet. Standard deviation of the heights of these trees. I go to this part of the island that I'm concerned about, and I take a sample of 42 trees, and I get a sample mean of 13.9 feet tall. Nothing amazing. So I just go in there. You can even see somebody carrying the little TI, and they just put all the shit into the list, and they make this. They get this information. Okay, and this we already know. Sure. If I want to construct the 98% confidence interval, heretofore known as CI for confidence interval, what z-score do I need to use? 2.33. How do I know I can use this number that came from the z-score chart? What part of this problem tells me I'm allowed to use the z-score chart?
98%.
No? What's got to be true for me to use the z-score chart? No. What's got to be true? It's on the very top of the chart. What's on the very top of the chart? A picture of a, so it's got to be normal. What part of this tells me it's normal? N. I like it. So it still has to be a normal distribution. So if N was less than 30 or less than or equal to 30, we technically couldn't do anything in stats 1. Okay, I like it. So notice most of your problems, they're going to have to tell you everything. The one thing you're going to figure out is what the z-score is. What if I would have said I want to make a 95% confidence interval? What would the z-score have been? 1.96, right? Do you guys see that? So how confident I want to be affects how far out I go, which affects how much data I catch, which is why I'm that confident. If I catch more data, I'm more confident that I caught a certain data point. Maybe. Okay. So now it's just plug and chuck. Now it's just plug and chuck. What's X bar? 13.9. Give or take 2.33. 2.91 divided by square root of 42. Okay. So what I would do first, let me see if you guys agree with this. This part of the equation here, we call this the error, right? So back in the day, I don't know if they still do this, but you would go to state fairs and such, and there would be a person set up there, and they'd say, "I'll guess your weight, plus or minus 10 pounds or whatever." So the plus or minus was the amount they were allowed to be off by. That was their error that they built in. You with me? Or they'll guess your age, give or take 5 years, which is a lot. But so if they say 32, then you could be 27 up to 37, and they would still win. Does that make sense? So this is why I call this the error. This is how much I think my mean is off by. So I would calculate this part first. What is this if you plug this into your calculator? What do you get?
.04
1.04?
or 1.05 if you round it.
1.05? Okay. Let's see. I think I agree. Yeah. Yeah, okay. Does that look good? And how do you do this? I love it. I'll never forget this semester somebody came up to me and said, "Where's my plus or minus button on my calculator?" So obviously you subtract and then you add, right? So what's 13.9 minus 1.05? 12.85. And what's 13.9 plus 1.05?
14.95.
Yeah. Okay. All right. So what is this? So here comes your, what's up? Is everybody all right? Is everybody roughly okay? I've taken a lot of stuff that we've done. Every part of this is old. but it's just the repackaging of it that's new. So here's gonna come the most critical part of this. You're actually gonna have to write a statement interpreting what this is. Oh, joy. I was hoping we'd have to do that. So, what is this? What does this mean? It's a confidence interval, yeah. So how confident are we that that interval catches the real mean?
98%.
Yeah, so we are 98% confident that the interval let's see, 12.85 feet to 14.95 feet contains what I'm gonna normally say here, if I'm not thinking about it, I'm just gonna say the true mean weight, and what I mean by that is the population mean weight. So I'll just put population here, but I might say true instead. The population mean weight of trees in that area. Weight, height. I'm thinking about the spiders. All right. I appreciate everybody remaining calm. This is very exciting. But what I want to point out is that little area we investigated on the island, we were concerned because there was some kind of a toxic spill or something, maybe. You with me? Maybe some passing thing, something washed up on shore and it kind of like seeped all over that area. So now I'm like, a couple years later, I'm like, oh shit, I think something's wrong with that area. So we go in. Let's say that the actual average of all the trees on the island is 16 feet tall. That's the average height. Did our research show evidence that there is a problem with the trees in this area? Why?
Because it's outside of the usual.
Yeah, the normal mean, 16, is well above what we consider to be the maximum possible value for the mean. What are the chances that this interval does not contain the real population mean?
0.0.
What are the chances it does contain it? 98%. So what's the chances it doesn't? 2% chance. So I feel pretty good about this. That's much better than my normal chance of being wrong about something. So I feel pretty good about that. You guys kind of with me? So is this proof that the trees' heights were affected by something? No. Hell no. It's a pretty good evidence that the trees' heights are different from the rest of the trees. Hell yes, right? You guys semi with me? This is a lot like the problem on the test, and I'm kind of happy that I did well. I never know if I'm gonna. I'm not gonna say that. The climate, the one about the temperature. We'll just stick to that, right? The numbers don't lie. The numbers don't spin. We do. So those are actual numbers that I gave you on that, and it's changed a little bit for different versions of the test, but they're basically the right numbers. That very last problem where I asked you, the last whatever 5, 6, 7 years, is that unusual? I like the idea that some of you guys actually constructed the what's unusual. You went up and down 2 steps, but the 2 steps you went were the new standard deviations. You basically did exactly this. You went up and down 2 new steps. Little tears came in. You basically did this early, right? You didn't have to, because the problem right before that, you calculated that it's basically a 0% chance that it was more than something, and then it said, well, the last whatever years has been more than this, and you're like, oh shit. That is evidence that something has changed, right? You guys with me? So the disagreement, by the way, just in case you're curious, climate change is real, there's no denying that. The disagreement is, do humans contribute to that, right? So I always love it when people are like, well, some scientists disagree, it's not settled. Well, that's 98% think it is, and 2% think it isn't. I'll let it go, okay. Then he starts asking people what shape is the earth. Okay. What would change if I made this a 95% confidence interval? What would change?
The interval,
What about it?
it would be like smaller.
It would be narrower, right? Which is a very cool word to try to say, narrower, right? You guys kind of with me? Why would that happen? If I did a 95% confidence interval, wouldn't it be a 1.96 here? Wouldn't this error be smaller then? I would go up less and I would go down less. Why does that make sense? If I want to be 98% confident, how much data do I have to catch? 90% of the data. If I want to be 95% confident, I only have to catch 95% of the data. So my interval gets a little smaller. You guys semi? So one example I like, even though I do not like to eat fish, right? I do not like seafood at all. I do like the example of if you're at a lake and you had a big fishing net and you want to be really sure you catch a certain kind of fish, you're going to cast out a wider net. If you're like, I don't care what kind of fish I get, you can cast out a shorter net. You don't care about a specific fish, like just give me some fish. If you want to catch a certain type of fish, you're going to cast a wider net. Does that make any sense? Because then you can just kind of weed out, there's a fish I want. Does that make any sense? So that's exactly what's happening here. If I want to be more certain that I caught a certain data point, in this case the mean, I'm going to make my net a little wider. If I can be less certain, I'm going to make it a little skinnier. Okay. I like it. All right. So this is going to have to be written at the end of any confidence interval problem. Okay. So let me give you this. Incredibly enough, I have a handout. Has everybody got their z-score chart, by the way? Okay. If you need to borrow a calculator, wait till I'm back up. Oh, we can do that like this. We're only going to look at the side that says 8.1. Don't worry about the side that says 8.3 yet. Yeah, give me a second. All right, let's see. We needed a z-score charts. We need a calculator. Make sure it's got battery. All right, before you guys get too deep into this, there's one more thing I want to do. I always forget to do this before I give that to you. Yes. Oh, of course. Make sure it's got battery. All right, real quick, one last thing that you need before you can do this fully. If I look at this formula, this part is the error, correct? Or at least, by definition, we call that part the error. So I could set up this equation right here. Is that cool? So for example, when the sample size here was 42, it led to an error of 1.05. If I made the sample size bigger, the error would get smaller because I would divide by more. Does that make sense? So if I have an idea of what I want the error to be, I can actually figure out how big of a sample it would take. If I wanted the error to be just 0.5, I would need a much bigger sample to get there. Does that make sense? Okay. So if I could solve this for n, I could then have an equation where I could plug in an error and see what sample size will create that. I call that a feasibility study. Have you guys heard of the words feasibility? If something's feasible or not? What does that mean? If it's possible, exactly. So if we were like, how many people do I have to talk to have this be within this much, and it turns out to be 12 million, that's not feasible for me. So I'm gonna let go of that error. I'm not gonna get there. You guys kind of with me? But if it comes out to be 100, I'm like, all right, I could do that, right? So, how do I solve this for n? And here's a wonderful thing from algebra. It's actually just from computational stuff. It's gonna be crazy, right? 10 divided by 2, what's that? Holy shit. What is 10 divided by 5? Holy shit. So if I have a ratio equals a number, these two things can change places because 10 divided by one chunk is the other chunk. Don't matter which chunk you're dividing by. So these two can just switch places. Very cool little shortcut to know. And then how do I solve for n? One more thing to do. Get rid of the square root. How do I do that? Square. So you get this equation. Alright, so that's that last problem on there. I actually prefer this format. I don't know why on the page I made it all, I distributed the square, but it doesn't matter. So please, dear God, help each other out. Work on that page. Let me know if you need some help. Okay. Oh, picture of mine. Plus, also, guys, most of you just learned about these things within the last half hour. Am I right? Did any of you? Some of you guys might have heard of these before, but how many of you have never ever worked with confidence intervals before? All right. So often this happens. We learn a new idea. I try to let you kind of play with it a little bit by yourselves. Then I come in and I show you more formal ways to do things and what to be careful about. And you see the mistake you made and why it makes it. Just give yourself some time. So that's why I like these kind of worksheets, because they're just playing around. You're just playing around with the ideas. It doesn't matter if you get it right. This is not graded. Okay. So I'm never gonna write this down on a problem necessarily, but the very first thing you should do in any math class where it's a lot of wordy problems, again, it's not a word problem, I should gather all the stuff they tell me. So what does the sample mean? Yeah, because average is another thing for me. The population standard deviation is, and the sample size is 37. So the most common mistake I see is some people just put all kinds of numbers here. Have you guys ever heard of the natural numbers? There's the whole numbers and the natural numbers and the integers. Have you guys heard of those? So it's kind of nifty. The natural numbers are what came naturally to us. So what came naturally to us is 1, 2, 3, which might explain why our number system is a base 10 system, right? So the natural numbers are 1, 2, 3. N really actually means a natural number. So we think of it as the number in our sample. So n has to be a whole number. It cannot be a decimal or anything. You guys with me? It's got to be a number of things or people. Okay. The z-score, I think we already did, right? For, what was this, 95? So in general, I figure out what is on. By the way, what is below that z-score there? What area is below the z-score up here? What area is below? More than 95, correct? What's the total area below the z-score? 0.975. Can somebody please look up, or let's do it together. If we look up 0.975, see if you guys can beat me. 975, let me take my time.
1.96.
Yeah, 0.975. 1.96. So again, it does not matter if you find the negative one or the positive one first, because you know they're both the same number. One of them is positive, one of them is negative, because of symmetry. Is that cool? I just normally go to the one that's most easy, which is just get that area instead of adding it. I just go to this one. So I happen to find the -1 first, who cares? Would I put in negative here? No, because the plus or minus is built in, correct? The plus or minus is built in. Go up and go down, because I have two z-scores. Are you guys doing okay?
Yep.
Now, I would never teach it this way, but this is a total plug and shut problem. And you guys have heard that phrase before, correct? I had one time a student thought I meant something else, and I don't know. So this is where you just plug values in and you chug the answer out, right? So if I plug numbers in, I get, what was it, 92.6, give or take, 1.96 of these.
4 point.
Is that cool so far? So again, 92.6. I'm almost certain that's wrong, because it came from a sample, correct? So the plus or minus is sort of as an improvement on it. Not only is it that, it's also communicating to somebody how certain I am about that. So if somebody came along and said, I made a confidence interval for dolphin lengths, it's anywhere from 50 inches to 110 inches. You're gonna look at them like, thanks for nothing, right? So more than likely, they didn't take a large enough sample, right? The smaller your sample, the bigger your error. So you're gonna get these stupid big confidence intervals. Are you guys with me? So if I take a larger sample, then my confidence interval starts to settle down because I'm less uncertain about my sample mean. I don't have to go out as far to cover my ass for that. Okay, maybe. So now I just figure out the error. I would highly recommend. So let me show you something I do. This is not that big of a deal, but it's actually kind of nice to know now. It does come in handy at several times. So let me show you some kind of nifty. And again, it's probably more nifty for me, but if I do 1.96 times 4.11 divided by the square root of 37, okay. There's that 1.324 thing that you guys were telling me about. Now watch. You don't have to do this, because you guys finished this problem, and a lot of you guys got this problem done. You did not do what I'm about to do. But just to show you, see the little button there? I can't remember if I talked about it yet or not. Stow, short for storer. So if I store that, and I have a lot of variable locations. See all the letters? They're all memory locations that I could use. But I go to the button I only have to push one button for, which is the X button. So now that's stored in X. So now I can do 92.6 minus that, and I can do 92.6 plus that. Right? You guys with me? And again, not a big deal. Who cares? But I just want to throw it out. Later this semester, our equations are going to get a little bit bigger. Right? So then we're going to want to know how to kind of control some memory stuff. So this is just me laying some groundwork for that. So what's the interval then from?
91.28.
Yeah, sounds good.
93.92.
Yeah. So let me say this right now. Normally I want at least as many decimal places in the answers as I have in the original mean. And really you should go one more place out. But if you said 91.3 to 93.9, that's fine. If you have the same number of decimal places as your original mean, is that cool? Okay. All right, so then how do we put together this statement? We are how confident?
95%.
95% confident.
That interval, 91.28
Interval 91.28 what?
to 93.
Inches to 93.92 inches. Does what? Contains the true mean length of dolphins. Alright, I like it. Now real quick, if I would have, and I swear I did this at some point, but I should have made this like dolphins in a certain area, so just go with me for a second. If I had this long kind of island, and one side of the island were these dolphins, right? And the other side of the island, I constructed a confidence interval for them, and I got 94.21 to 97.13. You with me? Okay. So one side of the island, I got that interval for their average length, and the other side of the island, I got this interval for their length. Is that evidence that the two sides of the island end up with different length dolphins? Do the two intervals overlap? Do the two intervals overlap?
Yeah.
What's that one go up to? 93.9 whatever, and then what's this one start at?
94.
All right, so do these two intervals overlap?
No.
No. So this is evidence that the mean length of the dolphins on either side of the island are different, which could mean some kind of difference in the available food, the temperature of the water even, who knows? Are you guys kind of with me? Okay. It's not the strongest evidence in the world. It's not a very big sample we took, correct? Okay, maybe. So I'm just trying to show you just the base construction of a confidence interval is pretty straightforward, but then what can we do with it after we've constructed it? All right. What is the probability that the interval we created does not contain the actual mean dolphin length? 5%. Kick ass. Okay. All right. So I love the questions I got on the next part. This is still the same problem, right? I've still got the same dolphins, it's still got the same information. The only thing that changes on part B is I want to be 90% confident now, right? It's the one thing that changes. So the mean is still the same. Standard deviation is still the same. I'm still talking about these same dolphins, right? But now what's my z-score gonna be? Yeah, how did you figure that out? So 90%, how much is out here? 5. And if you look up 0.05, you end up getting that funky little asterisk dude, right? Yeah. Now, let me show you something. So do you guys remember 98% was 2.33, right? 95% was 1.96. 90% was 1.645, right? Really quickly, look down here. See on the positive z-score side? I call it the little baby chart. Little babe, oh, don't even do it, Jeff. Little baby chart. Notice what it says. For 90% confidence, 1.645. Look at that shit. 95, 1.96, 99, that's one we haven't done yet, 2.575. Are you guys with me? Now, you know me. You've met me. I'm gonna ask you to construct a 96% confidence interval. You know I am. Or 94%, right? You understand what I'm saying? So if I ask you for one of these, kick ass, you can just go straight here. If I ask you for 96%, you gotta do it this way. So you have to know how to do it this way. Is that all right? Or is that understood, I should say? Okay. So our z-score is 1.645. So that's the only thing that changes. So now it's gonna be 92.6, give or take 1.645 of these suckers. Did anybody do this, get the error for this?
93.
Oh, what's the error, sorry?
1.111.
1.111? You're good, don't worry. So yeah, up here it'd be 93.711. And down here it would be
91.49.
489, is that right? I don't know. You guys with me?
Yeah.
Okay. And what makes sense? Which one of these two is my favorite word, narrower? Which one of these two is narrower? Sorry, can't see both. Yeah, because the first one starts further down than this one does, and this one ends before this one does. So this one lives inside of this one, yes? So this one is more narrow. There you go, Jeff. Just make it a phrase. More narrow. I like it. And then finally, if our boss says, it's not good enough, I need you to be within 0.5, so I'm going back to 95%, right? I don't want you to be within 1.32, I want you to be within half an inch. Like, oh shit. So now I'm like, how many dolphins do I have to do that? And again, I kind of like it better with the square on the outside. I don't know why I wrote it like that. So for 95%, what was the z-score? 1.96. Standard deviation was 4.11, and I want the error to be half an inch, 11. Yeah, you get like 259 point something, and you always round this up. Always round it up because it's the number of dolphins. I don't want you guys out there chopping poor little dolphins up. Let's round it up, make it a nice whole number of dolphins. Okay. So that, again, do we see this all the damn time? The concept takes a little while to discuss. The nuts and bolts of it, not that terrible. Maybe. Yes. Oh yeah, sure. My fault. I was zooming along up to this one. So how would I write this statement for part B?
We are 90%.
We are 90% confident. That
Interval 91.489.
the interval 91.489 inches to 93.711 inches contains true mean length of dolphins. Okay. You guys kind of with me? Okay. And the nice thing is, this is not English class, so it's completely fine to plagiarize a little bit. So whenever you're trying to construct the phrase for the ending, you can just go back to the question, right? We're so and such and so confident that our interval blah to blah contains the plagiarize. You're not really plagiarizing, you're just referencing what you were supposed to address, correct? Okay, lock up. Okay, now, one last thing. Well, it's a little bit involved, so don't get too excited. Any questions from this sheet, by the way, before I move on? You guys feeling better about this? So this is kind of built off of stuff we've done before to create these confidence intervals. And one of the most primary uses of confidence intervals is a lower level test of a claim. So somebody claimed that, for example, I'm thinking about this because I have this massive headache, but if somebody claimed that they had a headache reliever that would take my headache away, take the headache of anybody away in less than 12 minutes, right? So I give the headache reliever to 50 people, and the average amount of time it takes is 13 minutes, right? So let me write this down. So if they claim that it can take the headache away in less than 12 minutes, and I do a confidence interval and it's from 12.5 to 13.5, is that evidence that their claim is false? Yes. If the claim was true, this should at least have below 12 as a possibility. Does that make sense? So it is a first level claim check. Does that make sense? The next chapter is going to be the full freaking claim check process. This is a kind of first level claim checker. Okay. So, all right. Oh, Gucci out of the way. So, going back to my earlier real life example where some of you guys have seen confidence intervals in the wild when they're talking about polls for upcoming elections, right? So the plus or minus is down there. Now you guys know that's going to be part of the error. we need to develop the formula for how to do this kind of thing for percentages. So we can do this kind of thing, we can create confidence intervals for means. That's exactly what we're just doing. Now I need to construct a formula that can work with percentages. Are you guys semi with me? I know I said that a lot today. I'm really sorry. I got a major headache. I'm just trying to get there. So real quick, I started off with this formula before, right? That's where we kind of started. That was my kind of skeleton for moving forward. I wanted to start here. And so I said, we don't have the real mean, you have to use the sample mean, and that kind of led us down the road of how to construct the formula we needed. Can somebody remind me for a NPQ problem? Right, for an NPQ problem, what is the mean?
And times B
And what's the standard deviation?
for the NPQ.
Okay, cool. I love it. Okay. I don't blame you for knowing those. Those are the two best formulas we've seen yet for those things. The one major issue, do you guys notice how that's all about a population? If you go back, and in the future, if I ever remember this, maybe someday I'll remember this, every binomial probability problem you did, the probability of success they gave you was a population probability of success. It's a population percentage. I don't know if you guys realize this, but it was. So what I mean is, they would say like 11% of Americans are left-handed. That's what I said, the very first problem we did, right? That is describing a population. Are you with me? That would be a parameter, right? So just like before, we started with this and we said, well, now we're gonna have sample mean, so I need to have sample information in there. I can't use population information in there for the means, right? Same idea is gonna happen here. So instead of NP, the sample mean is actually, you're gonna really enjoy this. So P is the population percentage. P hat is the sample percentage. Right, and I'm not sure if you guys believe me, that is the symbol. I didn't just make that up myself. That is the symbol for sample percentage. So if I ask you, if I said I talked to 80 people and 40 of them like Shark Week, what's the sample percentage? What's the sample percentage I can create from that? I talked to 80 people and 40 of them like Shark Week. 50%. That would be P hat because it came from a sample. If I said 11% of Americans are left-handed, that is P, that's a population, right? So, I am going to use, let's just go this directly, watch this. So mean is NP, give or take, just like before, square root of NP cubed. But now, I'm going to say, well, we're going to use sample information instead, because that's what we're going to have. We're not going to have population information now, right? So if I wanted to find out what percentage of people it seems are going to vote for Jimbo, I don't know ahead of time what the population percentage is. I'm trying to get a feel for that. So all I'm going to have is the sample percentage. Whatever sample I talk to, I can calculate a percentage of them. All right, let me hold off for a second. So again, I started at the same place because what's this formula's job is to convert some value that I know how many standard deviations away it is into a raw score. That's what it does. So if I know how far up and down I want to go, I use this formula to convert it back to a raw score. But over here, we didn't know the actual mean. We just knew the sample mean. Therefore, the standard deviation had to change because we took a sample. We know it has to change. Here, I have the formulas for mean and standard deviation when I have a percentage problem, and it gets me in here. Now, this still is not good enough. I want to get to a place where I have a confidence interval like 55% to 60%. I want that to be the confidence interval. Are you guys are you with me? So I want to get to a place where I have a percentage, give or take some percentage. right? Like 50%, give or take 5%. So what do I not want here in my equation? I want a percentage here. What do I want to get rid of? N. So just to remind you guys, this captures the mean. And the mean is NP. So I think I didn't write this earlier, but the job of a confidence interval is to try to capture the mean. Right? So the job of this interval is to capture the NP, because that's what the mean is. If I divide everything by N, now I'm closer to where I want to be. I'm going to capture the real percentage. Can I just kill these two N's?
No,
Why not?
because it's one square root.
Beautiful, I love it. So I asked this morning, I asked my class, how many N's are on top?
Half.
Good, I love it. There's half an N on top, and there's a full N on the bottom, so of course they're not going to work. So they have to be in the same root before you can divide them, correct? So what is N equal to the square root of? Square root of N squared. So that's the same exact problem, correct? But now that I've written it under square root, I'm allowed to cancel. How many N's cancel? How many N's cancel? 1. How many are left?
One.
Where?
One.
Bottom. So then I get this. That looks funky as hell, which should sort of be a little expected. It's not going to be as straightforward as means. But we started from the same exact place. Are you with me? We started from the same exact place. We replaced everything with what we knew. Then we had to go to samples, because that's all we're going to have is sample information. And then I got it to be just about percentages. So whenever you see Jimbo is going to get 48% of the vote, and at the bottom you see plus or minus 4%, that's this piece. So if plus or minus 4 was too much, what can you do to make that go down? You can just take a larger sample, and that would make that go down. Just like we saw before, the error will shrink if I get a larger sample, because then I'm going to be more certain about what I see. Okay, maybe. So look at the other side of this real quick. Oh shit, I closed everything down. Oh yeah, so that's gonna come up. So I want to point out a couple things. We're gonna do this next time, but I want to point out a couple things. Let's see, yeah. There we go. So I'm still collecting my information. Can somebody do this? See, there's the sample information, right? What percentage can I construct from the sample information? No. That's how confident I want to be. What's the only thing this is going to do for me? Find the z-score. I love it. That's all that does. So one thing that definitely sucks about confidence intervals for percentages is that you're going to have a percentage you're trying to make a confidence interval for, and you're going to have a percentage confidence. You're like, oh shit, this guy only tells me what the z-score is going to be. Look at my sample. Can you say so many out of so many?
Yeah.
Okay, then you can construct a percentage, right?
So, yeah.
How many out of how many?
459 out of 650.
459 out of 652. That's the sample percentage. Why is it p hat and not just p? Because it came from a sample. Just like it's not mu, it's x bar if it's a mean of a sample. Same idea. So this would be 459 out of 652. And q hat, the great thing is, no matter what clothes they're wearing, p and q have to add to be 100% or 1, right? Thankfully, this is the only version of P with wearing a clothing that we're gonna have. We're not gonna have P shorts, we're not gonna have whatever. So it's just P hat. So Q hat's just gonna be 1 minus whatever P hat is, right? I like it. This is the big thing. So when I'm talking about means, what must be true for me to know it's normal? There's two things you could say. What should equal 1? you're thinking about for valid probability. When I'm talking about means, the problem we just did on the other side, how do I know it's normal? Either they tell me it's normal or sample size is bigger than 30. You with me? That's how means work. One thing we need to develop still for this is what do I check? And that's sort of like what this little thing I have boxed off is, and that's what we're going to talk about next time. We're going to have to figure out what tells me when an NPQ problem is normal enough. And I don't know if you guys remember that handout I gave you that had like the Mayan pyramid in the middle. It was about tossing a coin, and it looked pretty normal. I'm going to go back to that one to show us what I have to check to make sure this is normal. Why do I have to know it's normal or not? Because what do I need for the formula? The z-score. And where do I want to get the z-score from? The chart, and the chart only works if I have a... No, so I need a way to check if this problem is normal enough. Right, so we haven't developed that yet. So we have to do that. We'll do that. What was the other thing I wanted to point out? I forgot. We're still going to have the conclusion, all that kind of stuff. Okay. So, last thing, very last thing for today. Let me switch over. I want to show you one thing. I'm going to let us all out a little early. I let my other class a little early, which is fine. And you're definitely leaving early, because I don't know how much longer I can keep going. But I want to show you this. This is a study I found very quickly. Optimism is associated with exceptional longevity. I love that. If you look up any study, and what I like to do is I go to Google, I type in study, and then I restrict it to like last week. And what they'll do is they'll give me studies that were just published. And then what you always try to do is go directly to the journal where it was published, not some news outlet that's putting their own spin on the results. You go to the journal article itself. Always go to primary sources. Do you notice anything that looks familiar? There's a lot up there, I know, but let me point it out. So, I mean, all is a lot, and then right here, yeah, you will see confidence intervals at the beginning of statistical analyses, so that people know what, in this case, it's like basic demographics and such and health conditions of their sample. So it's one way to describe to people their sample they were looking at. So I just want to show you a real life in the world, in the wild kind of place for these confidence intervals. That's plenty for today. Thanks, guys. Let me know if you didn't get your test back or something. Otherwise, I will see you Wednesday.